I mentioned structure in the beginning of the lecture. The attribute value representation, there is no connection at all between the attributes. Each attribute is viewed in isolation. Sometimes you deal with data where that is not a good idea. Sometimes you actually want to have structure in the data, right? So maybe you're trying to model a tree, and an occurrence of A at this node is different from an occurrence of A at that node. A flat attribute value representation would not be able to capture that effectively. So the way you get around that is whatever structure you have in the data, whether it's chains or trees or anything, you have to embed it in the attributes themselves. So in this particular case, what I could do is, instead of taking nodes to be my attributes or node values to be my attributes, what I could do is I could look at sort of subtrees or paths from the root to the leaf. And then these paths would become the attributes, and I would look for whether they're present or absent in a particular tree. So for example, in this tree, ABA is present because there is a path that reads ABA. ABB is present, but ABC is not present. So that's a way to embed the structure into the attribute value representation, which is fundamentally flat. It doesn't want to have structure. So that's the way to trick it into accepting structure. That's structure in the input. Sometimes you actually have structure in the output. So you have a structured input X that you've represented in some way, and what you want to predict is another structure from it. Now that's not sort of a that's not a simple learning task. It doesn't predicting a structured output. It's not regression, and it's not simple classification either. So it looks like you couldn't use basic, or at least you couldn't use simple machine learning methods. But in fact, you can. But that requires a small trick. And the trick is, I really want to predict this structured output, but my classifier can't do that. My classifier can say yes or no. It can't output trees. So what I do is I embed a hypothetical output as another part of the input. And then I ask my classifier, is this a yes or a no? Right? Is the yellow structure, is the yellow output, does it look like a plausible thing from the blue input? That is a well-defined classification task. The answer to that is yes or no. And if it's a yes, then you output this hypothesis. And if it's a no, then you try another hypothesis and another hypothesis and another hypothesis until it says yes. So that's a way to trick your normal binary classifier into doing something really, really complex. Right? So, and it is used all over the place when you need to predict structured outputs. A good strategy is to actually embed the output in the input, and then you ask your classifier yes/no questions. Of course, what I'm skirting is the search over the possible hypotheses then becomes quite problematic, because there could be an exponential number of hypotheses, and you would have to iterate through all of them. But if your classifier is fast enough, then that is not actually a problem. Question? What if there are multiple possible output hypotheses? So that's actually not a problem, as long as your training data contains multiple examples with yeses. That's fine. Then it depends on, are you happy with just one plausible output, or do you really want all of them? And both of them you can solve with the right search. So the point is, you can use the classifier. It becomes a search problem.